Good morning, everyone, and thank you, Marta, for the introduction, and thank you for giving me this opportunity to share our recent results on FatNav, or Prospective FatNav motion correction. And yeah, my name is Krzysztof, and I work with in Chris Rogers' group. The basic concept of FatNavs we've taken from Dan Galician paper, in which he showed that for head motion correction, it may be quite beneficial to use the fat signal, which is located mostly around the scalp of the patient's head. And well, this signal is usually not needed for the host sequence, so we can get rid of this anyway by exciting this for the FatNavs. And also the signal is quite sparse, so even with really high grab acceleration factors, it's still quite readable. So we can acquire those fat navigators really fast. And in this paper, Dan showed that he can acquire a 3D GRE FatNav images in a bit more than 1 second. And such FatNav block can be inserted somewhere in the sequence, and well, in the worst case, the sequence has to be the TR of the sequence has to be slightly extended, but otherwise it's quite universal approach, and it works retrospectively, and we were able to reproduce the retrospective results. But what we are aiming for is the prospective usage of the FatNavs. So the basic scheme of the prospective FatNavs is quite simple. We have to acquire the reference FatNav image at the very beginning, and then after each slice or measurement, depending on where we embed the FatNav in the sequence, we acquire current FatNav. And then we have to reconstruct the image and register it with the reference one, and draw out the motion parameters and send them to the sequence for the prospective motion correction. And we did it, and it works. So you can see FatNav images in the top row and host images in the bottom row. And the FatNav images show the actual position of the patient head, and the host images are corrected. And on those two columns, you can see also comparison how the host images looked before correction. And yeah, you may ask, so okay, so if it's prospective FatNav, so how do we know how the host images looks like without the motion correction? And I think this is a good time to make a small philosophical interlude. So everyone knows this quote by St. Augustine, but it's not so clear when exactly he said that. And my gut feeling is that he must have been working on a prospective FatNav motion correction, and just someone asks him, okay, so Augustine, so how long it takes to reconstruct FatNav images and then register them? And he said this instead of saying that, well, actually we need about 2.5 minutes to do that, which is quite long, and it's not so prospective anymore when you consider this. So in the previous example, which I showed, this every second image was only corrected for motion. And we knew that from the very beginning that we will have to work on the performance. Perhaps we didn't expect that it would be so bad at the very first go, but we got a couple of ideas how to solve this problem. So the first one is to go back to the very fundamental properties of the K-space. And as you're probably aware, when we take an image and make a Fourier transform of this image, and then if we have some translations in this image, so the Fourier transform of the translated image is exactly the same as the one without translations, but just multiplied by the phase factor. So only the phase changes with the translations. And also with the rotations, it's even more straightforward. So if there are any rotations in the image, then the K-space is rotated by the same angle. So it's quite straightforward, and it should be quite easy to find those motion parameters directly in the K-space. So then we can get rid of both reconstruction and co-registration of the images. And for those who prefer rather plots and images than the equations, there's really simple examples of how it looks in 1D. On the left-hand side, you get original object and shifted object and their Fourier transforms. And on the right-hand side, you can see that if we take the FFT of the shifted object and multiply it by the proper phase coefficient, then we can reconstruct back the original image, or in this case 1D, but it works the same in 2 and 3D. And with the rotations, again, on the left-hand side, you get original object and rotated object, and you can clearly notice that the K-space of the rotated object is rotated by the same angle. There's a little problem when you rotate this K-space back to the position that it should be. So if you correct for motion in the K-space, because the reconstruction of the image might be disturbed with quite severe artifacts, as you can see here. The reason is mostly the problem with the rereading, and there are some different approaches how to solve that. Some are better, some are worse. The best one so far that we've tested was Pipe's regridding algorithm, which gives us, well, the images are fairly close to the initial ones, but it's still not perfect. But to be honest, we don't really care so much about the images if we want to just find the motion parameters in the K-space. So it's not that relevant, at least I hope. And yeah, well, the example with just the rectangle is quite straightforward and simple. When we take a look at the in vivo data and how the K-space looked like for the in vivo data, it's a bit more complicated. So here we got the reference scan and the rotated scan. And actually, what we also thought that in order to speed up everything, also the acquisition, we probably can not acquire the whole FatNavs, but we can take just the reference scan, which is a low resolution scan, which is fully sampled, and it's there for all the graph acquisitions. So perhaps those low resolution scans would be just enough to find the motion parameters. And when we tried, well, basically iteratively rotate this rotated scan and then subtract it from the reference one and search for the minimum in order to find the rotation angle. Well, there's clearly a minimum at the top row here. It's about -10 degrees. Our ground truth value here, taken from the fluid co-registration of the fatness, is about -12.5. So it's not perfectly accurate, but it's quite close, I would say. And this was done for the average of all 32 signals that we got from the 32-channel receiver coil. So we took a look at the reconstruction of the signals from particular channels, and here you can notice that there are some channels which are much more sensitive at the edges of the head. Some are much more sensitive right in the center, and perhaps some of them will be much more sensitive for rotations than the others. So we repeat the same experiment with iterative rotation of the particular of the signals taken from particular channels and for particular slices. And sorry about this plot; it might be a bit ambiguous, but here we got, well, basically the same as what I showed before. So just we take the signal from each channel and then rotate it a bit and subtract from the reference one. And the red lines show us the ground truth value. And well, we expect to find the minima somewhere near this ground truth value. And you can see that for some of the channels, there's clearly minimum right in this place where it is expected. For others, there are at least local minimas. For others, there are sometimes slight bands, so perhaps the second derivative would be equal to 0 in this place. So the information is there. So the question is, which channel should we use and how in order to find the proper rotation angles. And this is the same plot, but for all slices, so you can see that the tendencies are quite clear for some of the channels here, and for others, not so much. And then we can find which channels are the most sensitive for motion and also which slices. And quite interestingly, the slices in the middle are not very informative when we talk about motion. but the slices at the edges are much more sensitive to the rotations. And this is just the data from the slices and channels which gave out the best answer. So it was in plus minus ½ degree range from the ground truth value. And then we thought that, well, beside that, perhaps there are only some particular regions in the K-space that are the most sensitive for motion. So we checked those two funny shaped regions. So the ring ones on the left and the cross one on the right. And for the crosses, we took both, either just the data lying on the cross or just excluding the data on the cross and taking into account just the corners of the K-space, and repeated everything. And if you take a look at the signals reconstructed from just those particular regions in the K-space, you may find that for the rings, there are some channels which shows us those kind of like radar plots, and especially if you take a look at the channels 6 and 7 and those two columns. So there are some channels very sensitive in particular quadrants of the K-space. So possibly if we combine all of them in those columns, then we can find that they are quite sensitive for rotations, and then they can show us how the intensity changes when the patient head is rotating. And similar for the crosses, especially for the inverted ones, because, well, the signal in the middle of the K-space is just the low frequency signal, which is just a blob of a signal somewhere in the middle. But if we take those inverted crosses, so just taking into account the information at the corners of the K-space, well, there's information about the edges of the patient head, and this is perhaps the most informative in terms of rotations and well, translations as well. So just to wrap up, we got the proof of concept of prospective FatNavs, and now the only thing is to optimize the performance, and yeah, a bit just to invite you for discussion, and I'm really curious, what do you think about those approaches that we are testing at the moment? And also, what would you think about some of the approaches that we are going to test, like, for example, machine learning for that purpose, or a dictionary method, which could be based on acquiring a large number of FatNav images for a volunteer, rotating his head somewhere in the scanner, and building a dictionary with which we could compare later on during the prospective FatNav motion correction. Right, thank you. I'm happy to take any questions.